Hello everyone, my name is Jesper Jacobsson and I'm currently working as a professor at Nankai University in China. First of all, thank you for inviting me here today, where I'll give a few examples of what can be learned with the help of the Periscite database project. A few years ago, we were a bit overwhelmed by the number of papers in the Periscite field and how hard it became to get a proper overview. And we thought that it would be really convenient if all Perovskite data were to be found in one place. And we therefore initiated what now is known as the Perovskite database project. Our vision, when we set out, was to set up an open database where we could collect all Perovskite device data ever generated and connect this with graphical tools for simple and interactive searching, filtering and visualization. And as a part of that project, we manually collected device data for over 42,000 Perovskite solar cell devices, which basically was every device we could find data for up until spring 2020. And today I will tell you two stories about things we have learned with the help of this project, now when we have all this data consistently formatted in one place. But before I do that, if you are interested in knowing more about the Periscite database project, there is a web page which you find at www.periscitedatabase.com, and from that one you can access interactive graphics which enables you to filter and visualize the data, and from where you also can download the data or upload new data if you'd like to. And from the web page you can also access the papers connected to the project, as well as the source code for the project. The first story of today concerns external quantum efficiency, which is a standard measurement in the PV toolbox. And from such a measurement, you can extract a lot of interesting things. You could, for example, get data about the optical response of your cell, or the bandgap of your photoabsorber. You can get data about parasitic absorption and reflections, and get some hints about transport limitations and some other things as well. But one of the most common use of a measured EQE spectra is to integrate it with respect to wavelength under the assumption that you have AM115 illumination. And if you do this, you get an estimation of the short circuit current for your cell. And this short circuit current is often seen as a way to verify the reliability of IV measurements, which for the perovskites have been a concern due to, for example, high hysteresis, ionic motion, slow response times and degradation. And I would say it's usually taken for granted that the short circuit current from an IV measurement and the integrated EQE should be the same. And this similarity is, at least for established solar cell materials, assumed to be so robust that it's used as a basis for calibrating the light intensity in IV measurement systems. And if the two values aren't similar, it's usually taken as an indication that something has gone wrong. And this is also something that's been codified in the Periscite community in the form of, for example, various checklists which you need to fill in if you would like to get your data published in some prominent journals. However, there has been noted that it's not entirely uncommon with some discrepancy between those two values, at least for high-performing devices, as discussed in this paper a few years ago. But it was unclear if this perceived discrepancy just was a statistical anomaly or a tendency for the very best devices to be based on slightly miscalibrated measurements, or if it was an indication of a real effect based on some non-trivial physics. But now, with the Periscite database, we have close to 6,000 devices where we both have integrated EQE values as well as short circuit currents extracted from IV measurements, which allows us to look into this into some detail. And when we analyzed the data with respect to this, we saw that the short circuit current from IV measurements were higher than the integrated external quantum efficiency in 83% of all reported devices, and that the short circuit current from the IV measurements on average were 4% larger than the integrated EQE value. And I would say that if the average research group know what they are doing, and if they on average have succeeded in calibrating their equipment, and if you assume that errors are normally distributed, this translates to a 67% probability of measuring the short circuit current to be larger than the integrated EQE spectra, if everything is like it should be. And this means that either the Periscite community systematically has been calibrating the equipment wrong, or that there truly is a systematic difference between those two values. And if that is the case, we actually need to reevaluate some of the assumptions we have had in the field. Based on the data we have not been able to pinpoint the exact cause of this effect. We can speculate, but to really get to the bottom of this, we would need to do more dedicated experiments specifically focused on this. But we can, however, exclude a lot of possible reasons based on the data. We can, for example, say that this discrepancy does not depend on device performance, or on cell architecture, or on the choice of charge selective contacts, or on the perovskite composition, or on the perovskite deposition procedure, or really on anything we were able to check on. And this effect has also been persistent in time for almost a decade of experimental development, indicating that there truly is something interesting going on here. And I think that this is a pretty good illustration of what we could achieve based on initiatives like the Periscite database. At the start, we had a few people that had a suspicion that a short circuit current and the integrated external quantum efficiency may be a bit different, but there were no hard data to back up that gut feeling or that assumption. And if you're measuring it for yourself, it's very easy to miss due to the natural variability of those measurements. And if you see such an effect in your lab, you would probably discard it as a measurement error, because if you're only measuring a few cells, that is sort of a reasonable amount of measurement error, and you wouldn't have enough statistics to really say that something is going on here. But with all the data we had available, we could with high certainty say that something's really happening here, meaning that there is new physics that needs to be explored and explained, and that we need to update some commonly held beliefs and protocols in the community, which I think is a pretty interesting thing. And that concludes the first story of today. The second story is about device efficiencies and citations. What is the efficiency? That is often the first, and surprisingly often also the only question asked to the experimentalist. In the defense of that question, device efficiency is arguably one of the most important metrics for a successful solar cell. But it's not the only thing that matters, especially in a research setting where you may be looking at other things as well. But then in an academic setting, we have another measure of success, which is the number of citations a paper attracts. And reasonably, that should reflect values beyond just device efficiencies. But there is a rather common belief that device efficiencies have to be high for a paper to be taken seriously and for it to attract citations. And that is an assumption that actually could be explored based on the data in the Periscite database. It turns out that the Periscite database contains original device data from more than 7,000 papers. And we identified the highest performing device in each of those papers. And then we downloaded the corresponding citation data from Crossref from each of those papers. And at a first glance, we see that some papers get more citations than others. Some papers gain the status of breakthrough papers. And not surprisingly, papers with the highest efficiencies at any time tend to be among those breakthrough papers. So no surprises there. But if you look at it a little bit closer at data, we start to see interesting things. But we should remember that due to rapid development of device efficiencies and the fact that citations have a tendency to accumulate over time, we can't compare all data at the same time, so we have to bin it in some way. So I have analyzed data on a year-by-year basis. And when I do this, I see that papers with record efficiencies do, as expected, attract a lot of citations. But it's pretty far from a winner-takes-it-all situation. And the number of citations per paper is instead approximately following a log normal distribution with respect to the device efficiency, where the top papers, or the papers with the top 5 highest device efficiencies, are attracting around 20% of all citations. What may be more interesting than the attention given to top papers is how citations are distributed among the remaining papers. After all, most papers are by definition not top papers in respect to the highest device performance. And to analyze this, I sorted all the papers in order of their highest device efficiency, and then I plotted this against the cumulative normalized citation counts, which corresponds to the purple line in the figure on the slide. And what we see when we look at this is that the cumulative citation density takes the form of a fairly straight line for papers with lower device efficiencies, and that it bends upwards for papers with the highest efficiencies. This upward bend just mirrors the fact that top papers get a lot of citations. But what may be a bit surprising is how straight and smooth the part of the lower efficiency papers is, and how far it stretches. And this indicates that for papers that not are competing in the high echelons of device efficiencies, the device efficiencies may not have a very large effect on the number of citations your paper gets. And to analyze this in some more details, we can see that there is no clear-cut boundary for where device efficiency starts to play a larger role. But it seems to be something happening around the 80% line. So the 20% of papers reporting the highest device efficiency seems to behave somewhat differently from the rest. And if you just fit a straight line to the data, to the 80% of papers not reporting top efficiencies, we'll see a weak positive correlation that indicates that one extra unit, absolute unit of percent efficiency would give you 4% more citations, which aren't all that much. But what we see for the top papers, the 20% top papers, we see a steeper slope, indicating that 1% extra device efficiency would give you 65% more citations. But before you start remembering these values, I need to point out that the spread in the data is pretty large, and the predictive power of those straight fit is rather limited. So for the bottom 80% of the papers, the R2 value of the straight fit is actually only 0.02, which indicates that there is essentially no statistical significant correlation between device efficiency and the number of citations a paper will get. And I must say that is not exactly what I had suspected when I started this analysis, but that's what the data tells us. For the top 20% of papers, in terms of device efficiency, the R2 value is somewhat higher, it's 0.18. but device efficiency is also for those papers explaining only a small part of the number of citations. The specific example shown in this slide and the previous slides is for 2019, but the data, the trends and the numbers is pretty much the same regardless of which year you're looking at. And the take-home message from this analysis is that except for papers that report record efficiencies or close to record efficiencies, the device efficiency has little effect on the number of citations the paper will accumulate. Of course, a new record is basically a guarantee to citation in abundance. And it also turns out that a slightly higher efficiency may increase your chance of getting your paper accepted in a journal with a somewhat higher impact factor. But once it has been accepted there, it doesn't seem to have all that much of an effect of the number of citations you will get. So I would say that unless top-class efficiencies are within reach, an intense optimization endeavor to reach 1 extra % unit of absolute efficiency is unlikely to pay off in terms of more citations. That time that optimization would have taken may thus be better spent on the part of the work that truly provides more insights, for in the end, it's for that your paper is going to be cited, and it's that part people actually will care about. And that ends the second story of today. Before I end, I would just like to point out that the Periscite database project didn't end with the publication of the database, but it's still an ongoing project with a lot of different contributors doing different things. And if you would like to contribute with new device data, I would like to encourage you to do that, because if you do, your data get a new life among all the other data, and it could help accelerate the field even further. And with that, I have probably used up all my time. So thank you for listening. If you have any questions, please ask me now, or you could send me an email later.